Hi everyone, this is John Wen. In today's video, I'm gonna present an algorithm called LPOD, which stands for Local Path Based Optimization Scheduling Algorithm. This algorithm is proposed by our lab in Wayne State University. In today's video, I'm gonna split into two parts. For the first part, I will go through the details of the LPOD algorithm. In the second part, I will go through the code implementation of LPOD in Java. This algorithm falls into category 1 in our website, which is given a deadline D. We're trying to find a schedule that minimizes monetary cost while satisfying the deadline D. Compared with the previous work, ICP-CP, which is also presented in my previous video, this algorithm tries to make full use of leftover building cycle of existing VMs. Here is algorithm strategy, quite similar to ICP-CP. Firstly, it tries to distribute a deadline on each task as sub-deadlines, which is also known as LFT. And then it identifies all the partial critical paths in the workflow. And then we are trying to assign the PCPs to VMs sequentially. But here comes the difference from the ICP-CP. The LPOD is trying to let PCP make full use of existing VMs if they have leftover building cycle existing. That means in every PCP, we will check the task sequentially and see if there's any existing VM with leftover building cycle that is able to meet the task sub-deadline. If so, we are going to assign the task to that virtual machine until we cannot find any existing virtual machine with the leftover building cycle can meet the requirements. After all the tasks has been assigned in a PCP, we will adjust EST, EFT, and LFT for related tasks. So here is overview of the LPOD algorithm. In algorithm 1, it takes a graph and deadline as input. And then, firstly, it will form a list of tasks in a descending order of the priority rank, which is also known as upper rank. So here's how it calculated the priority rank. For the exit node, it will only calculate the execution time of the exit node. But as we know, the exit node always be 0 for execution time, so we can substitute 0 here. Otherwise, we will take the child node priority plus a data transfer time from the child node to the parent node, and we take the maximum and plus the parent's execution time, and then assign the parent's priority as this formula. So here is a formula how to calculate execution time. If there is no virtual machine type has been assigned to this task, we will always take the MET for this task. So here is MET, which means we take the minimum execution time of the task across all the virtual machine type. In another word, we take the fattest machine running time as the minimum execution time of this task. Otherwise, that means we have virtual machine type assigned to this task. We will use actual execution time of this task on that type of virtual machine. So then we will assign the EST and LFT for all the tasks. So you can see for the EST, which stands for the early start time, we calculate from the left to the right. That means we start from the entry node, we take the EST of the parent plus the execution time of the parents plus data transfer time from the parents to the child node, and we take the maximum to calculate EST of this child node. And for the LFT, on the other hand, we calculate from the right to the left, and that means we start from the exit node. We take the latest finish time of the child node minus execution time of child node minus data transfer time from the parent to the child node, and we take the minimum of all of these. So after we've done these two steps, we go into the line 5. We're trying to find all the PCPs based on this T-list. That is algorithm 2. So basically, it loops through all the tasks in this T-list. It always tries to find the children of this task and then assign to this CP, which stands for the critical path, until we cannot find any child based on current node, and that means this CP has been done. And then we add this CP to the PP. That means we add this partial critical path to the whole set of critical paths. So after the algorithm 2 is done, we are going to go to the line 6 of algorithm 1, which is path assignment based on this set of partial critical paths. That goes into the algorithm 3. So basically, in algorithm 3, it loops through all the partial critical paths. For every partial critical path, we check all the tasks inside and see if we are able to assign any task to the existing virtual machine with a leftover billing cycle. So you can see here, for every task, we check every existing virtual machines and to check if the available time is smaller than the early start time of this task, and also the leftover billing cycle is greater than the execution time of this task on this type of virtual machine, and also the FT is greater than EST of this task plus the execution time of this task on this type of virtual machine. If all of them are met, and then we will assign this task to this virtual machine. We take advantage of the leftover billing cycle until we cannot find any more. We will break from this for loop, and then we will call the assign path. So that means while we until here we have already take full advantage of existing virtual machines with their leftover billing cycles, and then we will assign a path to the new virtual machine. So this algorithm goes into algorithm 4, and algorithm 4 take advantage of dynamic programming, which means we don't know the optimal solution if we always take the greedy algorithm, because in scheduling problem of the workflow tasks, they always need to consider like the billing cycles. While there's always problem, we cannot make full use of billing cycles, so we cannot make always take the optimal solution or optimal steps while we look at the local optimal. So that's why we always we are trying to use dynamic programming to memorize the solutions, and then we track from the end to the beginning and see and to trace back into to get the optimal solution. So this is idea. So for the algorithm 4, this is assign the path of the rest of the partial critical paths. It basically loops through all the virtual machine type, and then we put every solution as a tuple in a TB table. So we take the first task from this list as a special case, because for this is the first one, we may need have a booting time considered. Also, we have to take care of the different for the rest of tasks. We have to take care of consider the parents virtual machine type, whether it's the same as a child node. But for the first one, we don't need to consider that. So the calculation of the TFT, which stands for task finish time, is calculated by the equation 16. That is the TST plus the execution time of task on this type of virtual machine, and the T left is calculated by the 20. So that is the T left of the first task is basically the time of the building cycle, how many building cycles it takes, and then minus the finish time of this task. And similarly for the task from the T2 to the Tn in this list, you will calculate the TFT as well by the equation 15. So here we take consideration of the virtual machine type, whether it is the same as a parent or not. If the parent virtual machine type is the same as a child node, we do not consider the data transfer time. Otherwise, we will take into the data transfer time into the TFT. So, and also if we looking at the TFT is less than the LFT of TI, that means we are going to meet the deadline of this task, and then we do the calculation accumulate cost by calculate 18 or the equation 19. So here is equation 18. That is, if we are have the TFTs smaller than the parent's TFT plus the parent's leftover billing cycle, that means we can still use this for free. Otherwise, we will calculate the execution time minus the leftover billing cycle, and over the billing cycle, then we get how many billing cycle we may use for this task, and times the virtual machine type price. So this is how it calculated. Firstly, take care of the first task, and then take care of the task from T2 to Tn, and put every solution into the TB table, and then we will trace back from the TB table to find the optimal solution. So here is a start. We start from the Tn. That means we start from the last task of the TB, and we always check the minimum or the minimum accumulated cost, and we get the top one from the list. So here is the updates of the TFT or the leftover billing cycle, as well as the provision time and deprovision time of the last one. That means we have choose that one, and then the rest of algorithm 4 is loop through the second last to the first of this assigned path. So similarly, we'll trace back the path assignment from the last one, and to calculate the lowest accumulate cost from the back to the beginning, from the end to the beginning, in a backward direction. So this is roughly how it does, and always update the LFT and the leftover time, and as well as the provisions updates and deprovisions updates as well. So you can see that here is an example that in this paper, listing this paper. So you can see it's quite similar to the ICPCP. You will always find the PCP and assign to the virtual machine, but the difference is while we assign the PCP, we can assign to different or multiple virtual machines. So you can see here the output is we have 2 virtual machine type 1 and 2 virtual machine type 2 and 2 virtual machine type 3, and we have the respective start time and end time, and we also have the internal cycle and the total cost, and which task is assigned to these virtual machines. basically we are able to, in the end, the PCP is like this. One PCP is T2, T6, and T9, and you can see this partial critical path is not assigned into single virtual machine because T6 and T9 is assigned to virtual machine 1 instant 1, but the T2 is assigned to the virtual machine 2 and instant 1. So that means we can split them into two parts, split a PCP into two parts and make full use of existing building cycle. So here is a performance matrix. I think this performance matrix is very good to consider, to prefer the workflow or the scheduling that meets the deadline, because you can see from the equation, if the deadline, if the make span is less than this one, we will have a base credits as 0.5 for the matrix. If it does not, we will have a 0.5 also as the upper bound of the performance matrix and minus how much make span it takes. So that means if we do not meet the requirements, meet the deadline requirements, we will get penalty. From longer make span we will have larger or bigger penalty. But if we are meet the constraints of make span or deadline, we will gain the credits. If we have less cost, we will gain more credits. So the author compares with several algorithms like the ICPCP and E2C2D. These LPOD have very good performance compared with the other two. So I think this is really good. So here comes a summary of LPOD algorithm. Firstly, it tries to distribute the deadline on each task as sub-deadlines, and then it identifies all the partial critical paths. And different from the ICPCP, it tries to make full use of existing VMs while assign PCP to VMs. So basically we'll sequentially check the task in a PCP and see if any existing virtual machine with leftover building cycle meets the task sub-deadline. If so, it will assign the task to that virtual machine until there's no more virtual machine can be available. Then rest of the PCP will be assigned to a new virtual machine. After all this done, we will adjust the EST, AFT, and LFT for the related tasks. So I think that's it for the part 1 of LPOD. Thank you so much for your time. I hope you enjoyed this video. Until next time, happy coding.